Hi everyone, my name is Christopher Tremblay. I am a first-year chemistry master's student in Heather Buckley's group. My studies are mostly electrochemical in nature, and my project focuses on the development of a sensor for in-field quantification of fluoride in groundwater. Fluoride exposure from groundwater is a serious health concern. If one consistently drinks water containing fluoride in concentrations greater than 1.5 milligrams per liter, adverse health effects can arise. These include dental and skeletal fluorosis, which leads to anemia, chronic pain, and in extreme cases, limb deformation. Looking at the map on the right, this phenomenon is more common in arid, low-resource areas, which make the conventional in-field analysis kit, Hatch, less than ideal. Hatch kits function using the SPANS reagent and zirconium dyes, which when in presence of fluoride change from red to colorless. The color of this resultant solution then correlates with the concentration of fluoride in groundwater. However, in order to utilize this method, a high level of chemical competency is needed, it produces hazardous waste, is susceptible to competing ions, and lastly, it is expensive. It costs over $2,000 per kit. These factors make the method difficult to use for those in low resource contexts. Hence, there is a demand for a simple, cheap, and greener in-field method for fluoride detection. Our proposed method utilizes optical fibers that have been coated with aluminum through sputter deposition. Aluminum metal is used as it is reflective and reacts with fluoride to form AlF3. As such, it will dissolve in the presence of fluoride. So, the method functions through sending light down a fiber into a splitter, which is then connected to the coated aluminum fiber and a photodiode. When this aluminum surface on the end of the fiber is intact, light reflects back up through the fiber, going into the splitter, and is redirected to the photodiode. The photodiode then measures the intensity of light coming back up through the fiber and gives a voltage reading. So, when this aluminum surface corrodes in presence of fluoride, the intensity of light reaching the photodiode will then decrease at a given rate. A diagram of the system is seen in Figure 4. This rate of corrosion has been found to correlate with the concentration of fluoride in groundwater and allows this analytical method to determine fluoride concentration down to 1 milligram per liter. Since the method functions primarily on the corrosion of aluminum in presence of fluoride, it is important to understand the mechanism in which the corrosion proceeds. Electrochemical impedance spectroscopy has been used as the primary method in this mechanistic study. The figure shown in panel 4.1 shows the impedance spectra of a sputtered aluminum surface in 1 parts per million fluoride from 10 kHz to 1 mHz. The double capacitance loop seen in this spectra is indicative of pitting corrosion, as the first loop shows the capacitance of the metal corrosion and the second shows the capacitance of the pitting corrosion. This lines up with the fitting from the equivalent circuit seen on the right. The data shows us that as time proceeds, both capacitance loops grow larger, indicative of more corrosion occurring due to a larger surface area for double-layer capacitance. In order to verify that the corrosion was proceeding through pitting, atomic force microscopy was used as a qualitative observation of the mechanism. After 24 hours in 1 ppm fluoride solution, 15 to 20 millimeter deep pits can be seen forming on the surface. Now that it is known that the mechanism proceeds through pitting, it is clear that the previously used single-mode fibers are not suitable for this method. Since the pits are about 5 to 7 microns in diameter, the 9-micron core of a single-mode fiber will cause too much variability in the analysis. Therefore, we are moving towards a system that uses 400-micron core multi-mode fibers, which will allow a statistically significant amount of pits to form on the surface during corrosion, reducing variability. In addition, multi-mode fibers are compatible with LED lights, allowing us to move to a more portable system and reduce costs. Overall, we are working on providing a new in-field sensor for fluoride, which can be utilized in low-resource contexts. Ideally, our method will be green, effective, and cheap. It will allow communities to make their own democratic decisions about their water quality, without having to send samples off to a lab to be processed or calling in professionals to do their water analysis for them.